Okay, any questions before we get started? So we were on oxidation state 2 functional groups. We're going to look at one of these conservation reactions. Then we're going to do some more additions, and we'll spend quite a bit of time today on imines and enamines. So an imine is the carbonyl, the nitrogen equivalent of a carbonyl, so a CN double bond. And then an enamine comes from a carbonyl group, but the starting material is a little bit different. So we're dealing with how nitrogen compounds condense with carbonyls. So we had left off on this proposed reaction where we had this ketone with 2 ester side chains forming a ketal. So remember those words acetal and ketal. And the issue was that central carbon atom is at oxidation state 2 as a carbonyl, and then it remains 2 in the product. These carbons of the esters were 3, and then they become 1 in the product. So the issue is we need to reduce the esters in the presence of the ketone, but the only thing that reduces an ester is lithium aluminum hydride, and that's strong enough to reduce the ketone at the same time. So we have this challenge. And to overcome that and retain the oxidation state 2, we have to protect it first as the ketal. So when we scan our list of reagents, it looks like we could start with F as step 1. So CH3OH in acid. So all we're doing is changing that hybridization from sp2 to sp3, and then we're sprouting off 2 equivalents of methanol. And now the ketal is safe from nucleophilic attack. So at this point, we can do step 2, which is the lithium aluminum hydride reduction. That'll take the esters down to the primary alcohols. And so really we can sort of get away with just doing one more step. The acetal is sensitive to acid, so it's going to deprotect that to the ketone. But at the same time, we have these floppy arms of the primary alcohols. Because we're under acidic conditions, these are just going to snap back shut on that ketone, and that would give us our final product. So for step 3, we can just treat with acid and water. And the equilibrium will drive those side chains to cyclize to the ketal. In Module 4, we'll get into something called polyketide synthesis. And really what that is are just natural products that occur in plants or marine organisms. that have oxidized carbon atoms along their backbone. So we'll learn about the relationship between alcohols on a carbon backbone, and when they're oxidized, how those things form ketals with one another. So again, this problem I think nicely highlights the reason why you need to do protection so that you can conserve, again, this oxidation state 2 in the presence of starting with something higher. So that's the addition of oxygen to a carbonyl. The next reaction we're going to learn is the addition of cyanide, so CN. So notice we have sodium Na+, CN. The carbon is actually bearing the negative charge. So it's a carbanion, but it's not a strong one. It's a weak nucleophile. So again, with these weak nucleophiles, they can hop on and off due to equilibrium. So when that adds to the carbonyl, we get the nucleophilic addition. That generates O-, which is then just protonated by the base or acid there, sodium bicarbonate. And so what we end up with is called a cyanohydrin. Hydrin is just an old-timey word for alcohol. Another way to phrase this is alpha hydroxynitrile. So this does a couple things. The carbonyl goes from oxidation state 2, then to 1, but the cyanide is at oxidation state 3. And so that is functionally equivalent to a carboxylic acid at the same oxidation state. So you can transform the nitrile into the acid. And the basis for that, we'll see in a couple slides, is pretty important. Any questions? I already kind of showed it to you. It's pretty easy. It's just cyanide, nucleophilic attack, and then a protonation. So I think I have the mechanism, but so as I mentioned, that carbon of the nitrile's oxidation state 3, that can be hydrolyzed with acidic conditions, so sulfuric acid, or basic conditions, sodium hydroxide in water at really high temperature, so above the boiling point of water. So we call those forcing conditions because you have to add a lot of heat to this. And what's happening is you're hydrolyzing the nitrile to an acid. While maintaining that oxidation state. So what's nice about that is lithium cyanide, sodium cyanide, potassium cyanide, they're all solid reagents. You get a bottle of it, you weigh it out. It's pretty easy to run that. To make this product, this alpha hydroxy acid, there's really not a good functional equivalent where that carbon is nucleophilic, but it's existing as a carboxylic acid. So what I mean by that, so we have cyanide, which is this. That carbon's nucleophilic. That does not exist as a nucleophile. So if you want to make it, you essentially have to do these two steps. You're adding the carbon at the correct oxidation state and then hydrolyzing it. So we can rationalize why this doesn't exist. I mean, you have a very acidic proton here. You can't have sort of a strong carbon nucleophile / base in the presence of an acidic hydrogen. So that reagent, it doesn't exist. Overall, the strategy of adding the cyanide to the carbonyl is a pretty important one, because as we'll see, it's going to allow us to make amino acids. And so those are the monomers of proteins. So an amino acid is an alpha amino acid. What you see here is an alpha hydroxy acid. So the question is, how do we make this into an amine, NH2? So to do that, we first have to change the carbonyl into the nitrogen equivalent, an imine. So the mechanism of that hydrolysis, I'll let you write it out on your own. It'll probably take up the whole page. But really what it is a series of proton transfers. You have to take the nitrile and convert it into the acid. So this carbon in blue becomes that carbon. What you see, you're losing nitrogen, and then you're adding essentially the equivalent of water to it. So overall in your mechanism, you need to generate ammonia as a product. That's the nitrogen basically gets incorporated into that, and that's how you get it out of the molecule. But it's initiated either under acidic or basic conditions, and really you're looking for proton transfers. The oxygen atoms come from water. So plug through that, see if you can figure it out. If you have questions, come see me during office hours and we can discuss it. The main thing to remember is under acidic conditions, things have to be neutral or positively charged. Under basic conditions, neutral or negatively charged. So at this point, we're going to look at nitrogen nucleophiles adding to the carbonyl. And then once we form that species called an imine, we're going to further add nucleophiles to that. So mechanistically, it's the same. You still have a double bond to a heteroatom, and then you're just going to add some other nucleophile to that. The first reaction, to put this into context, that we're going to look at is called the Strecker reaction. And so the Strecker reaction will make an alpha aminonitrile. But as we saw, the nitrile is a functional equivalent to an acid. So once we have that, we can hydrolyze it to the alpha amino acid. And again, those are the building blocks for proteins. So the way this will work, we start with our functional group. I'm going to show aldehydes for this purpose. We have oxidation state 2. We're going to treat that with potassium cyanide in the presence of ammonia water. The first thing that will happen is the ammonia will condense to form an imine. So notice this word imine, I-M-I-N-E. So an amine condenses with a carbonyl to form an imine. So that's a CN double bond. And this is primarily how nature does this to get nitrogen into molecules. It forms imines and then reduces them. So same electronics as a carbonyl, basically. The carbon's delta plus. Nitrogen has a lone pair. It's delta minus. So the cyanide will then attack that carbon. And so the product now, we see there's the alpha carbon, so alpha amino, and then the nitrile. And again, acid or base. That will make an alpha amino acid. So on the next slide, I'll show you how the imine forms. We'll walk through those proton transfers. Then the addition of the cyanide is just the same. So when ammonia condenses, it's we're going to have the lone pair of the nitrogen attack the carbonyl carbon. And then once that happens, we have to protonate the negative charge on the oxygen, do some proton transfers, and then eventually the oxygen will leave as water. So the first thing we'll do under these conditions maybe a way I want to write this. I'm going to write it as ammonium hydroxide. All it is, if you take water and you bubble ammonia gas through it, that'll form ammonium hydroxide. Any gym bros in the crowd throwing up a couple 100 pounds, need some smelling salts. Typically those smelling salts are ammonium based. So ammonium hydroxide is super pungent. Just a whiff of it will wake you up pretty quick. So the reason I want to write that like that is I want to protonate the carbonyl oxygen with the ammonium plus species first. So NH4 is an acid. And so we can protonate it. And so now that generates ammonia. So that's our nucleophile. We'll attack the carbonyl carbon. And so we're going to use that hydroxide to help us move the hydrogens around. Because right now the nitrogen is plus charged. It needs a lone pair so that eventually it can push out that oxygen. So that'll get the lone pair. So one thing I want to point out, so again, we started at oxidation state 2. Now we're ending up at 2, but the hybridization's changed. Because you have this sp3 hybridized carbon, but now the heteroatoms are different, it's no longer called an acetal. It's called an aminal. So A-M-I-N-A-L, aminal. Acetal implies that both heteroatoms are oxygen. Aminal, one is O, one is N. So at this point, the lone pair of nitrogen can collapse. We can push out hydroxide. The nitrogen becomes plus. We generated hydroxide that can do the proton transfer. So that will generate our imine. So I know the words are kind of clunky, aminal, imine. Just make sure you know what they're implying in terms of the connectivity. And so that, again, is the nitrogen equivalent of the carbonyl, so the cyanide will now attack. And then we just end up doing a proton transfer. So again, as we move forward with the different oxidation state 2 carbonyls, aldehyde or ketone. Now what we have to pay attention to is the class of the amine we're starting with, whether it's ammonia, primary, or secondary. For these reactions, we're not concerned about tertiary amines. They will not undergo these reactions. So the imine is one part forming that, and then the Strecker, you're adding cyanide to it. That gets you your alpha aminonitrile, which is the alpha amino acid equivalent. Questions? So for the most part, the mechanisms all kind of have a common theme. There's this nucleophilic addition, but what's really new now is understanding the proton transfer parts. So I'm going to introduce amino acids now. What are they? But we're going to return to them in Module 5. So any amino acid you see up here, you can make through the Strecker reaction. They have the commonality of the alpha amino and then the acid part. What is different is the side chain. So up here, I've indicated that as R. So nature uses 20 what are called proteinogenic amino acids. There are unnatural amino acids that can be found in trace amounts, but these are the 20 common building blocks for making proteins. And it turns out that living organisms on this planet, I'm not speaking for other planets because we don't know, we all use the S amino acids. That alpha carbon is a stereocenter. You have an acid, an amine, a hydrogen, and a side chain. So 4 different substituents. It's a stereocenter. And all of our proteins, the naturally occurring ones use S, except there's one where that center is R. And as we saw, sort of, I think at the tail end of organic 1, a way to represent stereochemistry is to use the Fischer projection. And what this is, sort of like a cross notation. If you put your eyeball right here, and you look at this bond, if you could imagine taking that left structure and just sort of rotating it, that amine ends up to the left. The hydrogen that's back ends up to the right. The acid's on top and the side chain's on the bottom. In a Fischer projection, remember we talked about nomenclature, and the parent compound or the parent name always has the highest oxidized carbon. In a Fischer projection, the highest oxidized carbon is always shown on top. So you have this is the chain or the backbone that's vertical. The highest oxidized carbon's on top. And wherever there's a horizontal line, that indicates that carbon where they intersect is a stereocenter. So what does that mean? Because we know that carbon isn't flat. So that is equivalent to the stuff on the horizon is projected out towards you. And then on the vertical, they're going away from you. And we'll see the reason why Fisher used these when we study glucose and how he was able to figure out what the structure of glucose actually is. So you have the amine, the side chain, the acid, and a hydrogen. And so that, again, that hydrogen, that's coming from the aldehyde. The NH2 comes from ammonia. The acid comes from the nitrile, and the R side chain is the rest of the aldehyde in the Strecker reaction. So within the 20 amino acids, they're classified 4 different ways: nonpolar, polar, acidic, and basic. So these are the names. And if you go on to any other classes, biochemistry, cellular and molecular biology, any of those, glycine, alanine, valine, leucine, isoleucine, methionine, proline, phenylalanine, tryptophan. So 5 minutes just passed by me reading those. So in those classes, those are abbreviated into 3-letter codes, and then they're further abbreviated into 1 letter. So as you learn proteins, those letter sequences represent amino acids. And it's important to know the classes because really what it's looking at is the side chain. The functionality of the side chain determines where it falls in these classes. So just to introduce these to you now, and when we get to Module 5, we'll talk more about the structural features of them. The nonpolar amino acids, glycine, or GLY, that's the 3-letter, or G. The side chain is 2 hydrogens, so it does not have a stereocenter. That's the only one that does not. And maybe what I'll do is I'll just highlight the side chain in red. For alanine, it's a methyl group. For valine, isopropyl. Leucine, it's 4 carbons, isobutyl. Isoleucine actually has 2 stereocenters. This is secondary butyl. Methionine has a sulfur in it. Proline is the only one where the side chain and the amine are cyclized, so it forms a ring. And it's the only one that's also a secondary amine. All the others are primary. Phenylalanine has a benzyl group. And then tryptophan, this ring system here is called indole. As that side chain. And so those are all considered nonpolar. By nonpolar, you can use other words, say lipophilic. So lipo means fat, philic means loving, so fat loving. And really what the side chains are doing is, if the cell is an aqueous environment, where are these side chains? Are they pointing sort of out of the protein or in towards the protein based on the aqueous or ionic environment it's present in? So polar amino acids, asparagine has an amide. So we have a primary amide. Glutamine is another amide, but now the linker is longer. So you have this 2-carbon linker rather than 1. Serine has a primary alcohol. Threonine is secondary, has a second stereocenter as well. Tyrosine looks like phenylalanine, except now you have an aromatic alcohol. And then cysteine, notice the stereochemistry there, that's when it inverts, it's R. So that's the only one that's R. And again, that's based on the CIP rules about assigning priority. So serine and cysteine, one's an alcohol, one's a thiol. Now the two acidic ones, aspartic acid, so it has a second acid. Glutamic acid, second acid again, but the linker is now longer. So when we do get to studying these more in depth, what we'll talk about, you have OH, OH, NH2. We'll talk about pKa's and doing acid-base titrations of amino acids. Because ultimately what that will tell us is what is given a pH from 0 to 14. Is that NH2 protonated? Is it neutral? Is the OH deprotonated? What is the charge of the amino acid? And then the basic, this thing here at the end of arginine, that's called a guanidine. So the guanidine has these carbon linkers. Histidine I talked a little bit about in terms of nitrogen basicity. So that's the imidazole ring. And then lysine has a second primary amine at the end of its side chain. So as we learn more about those, we'll learn how to condense them. As you condense more and more amino acids, eventually you can form a protein, which is a biomolecule. A protein is essentially a large molecule in your body that carries out a specific function. Another word what we use for that is enzyme. Questions? So remember in the last module, we ended on how do we get nitrogen into a molecule? So we saw sodium azide, potassium phthalimide, sodium cyanide. Those introduced nitrogen into the molecule, but they had to be protected. We deprotected it to get a primary amine. What if we need to make a secondary or tertiary amine? We can't use those other reagents. So we have to use a different method, and this is where these condensations come into place. So overall, the name of this is called reductive amination. We're going to take a carbonyl, condense it with some sort of amine, and then we're going to reduce that. So that'll get us into secondary and tertiary amines. The complicating factor of this now, it's really important that we analyze what we're starting with in terms of the carbonyl component and the class of the amine, because we can form either the imine or this other functional group, enamine. So an enamine is an alkene with a nitrogen bonded right to it. An imine is a carbon-nitrogen double bond. So we'll start with the imines. And I'm going to draw a line right here. So on the left, those come from aldehydes. We can see the oxidation state 2. We look to the left, we look to the right, we see carbon hydrogen. Then on the right side of the slide, there's our oxidation state 2. Now when we look at what's bonded to that, it's carbon and carbon. So that's visually what you're looking for. What component are you starting with, an aldehyde or a ketone? If I dissect the double bond like that, I can say that's coming from an aldehyde. Then the amine component is coming from ammonia, NH3. If I do the same for the other one, I can tell that's coming from methylamine, H2N CH3. So if I take an aldehyde plus ammonia and I condense them together, I get that imine. And then the byproduct is water, H2O. So this is part of the table we'll fill in. So amines can start from either an aldehyde or ketone, condensing with only a primary amine. So within that, I'm including ammonia. So what is the difference? See the NH3? Notice it's left with a single H. NH2CH3, that's retained. So these two H's and then the O from the carbonyl are what's lost as water. Now thinking forward, a secondary amine only has one oxygen. A secondary amine only has one hydrogen. So the question is, if you're producing water as the condensation byproduct, where does that other hydrogen come? So that's why we have these two classes, enamine. So I'll just write a quick note here. So primary amine, secondary amine. So it's important to understand those classes so you can correctly predict what product is going to be formed. The ketones, you can do the same thing. Dissect those double bonds. And that comes from ammonia. That comes from methylamine. So when I draw the structures out, we look at that, we see the oxidation state 2. We can see that ammonia plus the aldehyde condense to the imine. And again, that byproduct is water. So we can eliminate B and D. Then we need an aldehyde, so we eliminate C, and we end up as A as the correct product. So the key thing to remember, you have to start either with an aldehyde or a ketone. A primary amine gives you an imine. Now, if the amine is secondary, you get an enamine. So all that is, it's an alkene with a nitrogen bonded to it. So what is the difference between primary and secondary amines? Why do they give these different products? If we look at the carbon that's bearing the nitrogen, I'm going to think of that carbon as at oxidation state 2. So if I dissect that, what it's telling me, it's coming from an aldehyde. So a 4-carbon aldehyde. Then the amine, nitrogen, 2 methyl groups, and then an H. So it's a secondary. So you see what the issue is. There's only one H on that nitrogen. We have an H, we have an O, so where does the other H come from to get water?
The neighboring carbon.
Say it again?
The neighboring carbon.
The neighboring carbon. You see how there's this double bond now, carbon-carbon double bond? We'll see a little bit in a couple minutes. The carbon next to a carbonyl is called the alpha carbon. So if I compare these two, there's the oxidation state 2. But now in the product, there's a double bond. So this alpha carbon here, it starts with 2, it loses 1. So there's where the second H for water is coming from, the alpha carbon. Now, a complicating factor of this, as you see, these are the same molecule, but they're geometrical isomers. This one's called E, that one's called Z. Those are just the German designations for cis and trans. So Z is the equivalent of cis, and E is the equivalent of trans. So again, how do we figure that out? I'll put in blue these 2 carbons here. Those are the carbons of the alkene. Then for each of them, you have to assign a priority based on the groups directly bonded to that carbon. You have nitrogen and hydrogen. And you're just following the periodic table. Nitrogen has a higher priority, so we assign it to 1. So 1, that's 2. If I draw this hydrogen in, now we do the same thing for the other. We have carbon versus hydrogen. So 1 versus 2. And then you say, are the ones on the same side or opposite? So in this case, they're on opposite, so that's the trans. So you can call these geometrical isomers or configurational isomers, either way, but that's how you assign E, Z, or cis and trans. Notice with our aldehyde here, you have that hydrogen and that carbon. So there's only one alpha carbon. So that was with an aldehyde. Notice now what gets tough about it is when you have a ketone, you have two alpha carbons and they can be different. So that's why we get this mixture of different alkenes. So we talked about alkene substitution way back in organic 1, mono, di, tri, tetra substituted. If I do the same analysis here, I'm going to dissect that line, that bond. That's telling me that this is coming from a ketone. And then the same amine, dimethylamine. But why are there 3 products now? Because we have an alpha carbon, and I'm calling that alpha prime because they're different. One's a CH3, one's a CH2. So we already stated that that second H for the water is coming from an alpha carbon. That necessarily is going to give 2 different types of alkenes. And then when you throw in the geometrical isomerism, that's giving you the third. So notice this one. I'm going to say the less substituted alkene. That's coming from the methyl group. So there's no E and Z for this because both substituents are hydrogen and hydrogen. If you go from alpha prime, that's when you can get E or Z.
Dr. Gunny, what is it called again when one of the carbon on the alkene is only hydrogen and hydrogen? Is there a term for that?
I'm drawing a blank. I'm sure there is, but. Well, like I would say on this carbon, since you have a substituent and a substituent, I would say, yeah, that's geminal substituted. So geminal means 1, 1. And then the word vicinal means 1 and 2. So I think on the next slide, draw the mechanism, but the question is, why aren't tertiary amines? So if we had, say, a common reagent is triethylamine, that's a tertiary amine. So why can't we use those? That nitrogen has no hydrogens on it. So there's no possible way you're going to get the formation of water using that. So let's see how we get the formation of the alkene. Why is it doing that?
And the naming, what N means?
So this means, so normally like with carbon, like on a carbon backbone, you're using a number to specify like a substituent. When you have nitrogen, see how it says NN dimethyl? So that's essentially telling you both methyl groups are bonded to the nitrogen atom. So it gets a little funky like that when you have larger molecules with a lot of substituents. Sometimes you'll see those italicized heteroatoms, like oxygen something or nitrogen something. But it's telling you whatever comes after that is on that heteroatom. Yeah, we're going to, and So I'll just draw that as one of the products, and then I'll show you the divergence point where you can get the other ones. So typically when you run these, I'm going to say we're going to use this reagent toluene as a solvent. And then we're going to heat it pretty high, 120 degrees. And again, the reason for that is because we're generating water, and we want to remove that water. So I wrote this as dimethylamine.HCl. So that's dimethyl ammonium chloride. So I'm putting it in there so I can use the HCl to help protonate, move hydrogens around. So we have an acid, and our carbonyl oxygen is going to be the base. So we'll protonate it. So that activates it. Now we can have the dimethylamine attack that. So we'll do some shuffling of the hydrogens around now. We have to get one off of the nitrogen so it becomes neutral, and then one onto the oxygen so we can get rid of it. So I'm going to write just PT for proton transfer. So that generates HCl. And then we'll use that to protonate the oxygen, yep.
Where did the hydrogen that's bonded to the carbonyl carbon come from?
This one right here?
No, the next one.
This one?
No, the one to the right.
This one? Sorry,
Sorry, the step, the last step,
this.
the one just down to the right, connected to the old carbon.
Oh, sorry. I was... It's not going to let me erase that now. That should be carbon. I switched in my mind to an aldehyde for some reason. So we're going to protonate the OH. And so now the nitrogen lone pair can eliminate water. So that forms the double bond. That leaves is water. So I'm going to put minus H2O. So you see what the issue is, right? We're left with this positively charged nitrogen. So that looks like an imine, but it's positively charged, so it's called iminium ion. So nitrogen, carbon double bond, 2 carbon substituents plus charge iminium ion. So it's not neutral, we're not done yet. So this is why we have to eliminate from the alpha position. We have that alpha carbon, that alpha prime carbon. So I'll draw 1 hydrogen coming off. The chlorine can abstract that. We form the double bond, and then nitrogen gets its lone pair back. You would form the 2 other alkenes by eliminating from the alpha plus, which is the methylene group. Yeah.
Can you use like a larger acid or something to make it more selective in this process? Like what we learned about E2, E1, something like that.
Yeah, so that's the main crux of the issue. I'm not sure we'll have time today, but when you get into these situations where there's 2 alpha carbons and you only want to deprotonate from one side, so this side or that side, this side is going to give you the geometrical isomers. So again, based on the nature of the acid you're starting with, you can start to control these things to some extent. And to really do that, there are fancy reagents like fancy organic acids, but really it's better controlled when you have Lewis acids, like things like boron and aluminum. Then you can really go after one in preference to the other. So again, that's an amine. So don't let that fall out of your head because we'll revisit enamines in module 4. Yeah.
Could you go back to the last slide? I'm confused.
So we have a ketone. And a secondary amine. So what do we think the product is? So B as in boy. So here's the second oxidation state 2 carbon. It has alpha and alpha. So what's an easier way to remember this? The double bond has to end up between the oxidation state 2 carbon and the alpha carbon. C and D are wrong because of the placement of that double bond. A is an intermediate in the formation of B. So that would be the iminium ion. So this is when the base comes along, abstracts the hydrogen from that alpha carbon. So as I said, in Module 5 and then your biochem classes, if you go on to them, this is how nature introduces nitrogen into a molecule, through a condensation reaction like this. So iminium ions are pretty important. If you've ever drinking a beer in your life, or whiskey or whatever your poison is, so the alcohol in that is ethanol. So any liquor or beer, it's always ethanol. It's depending on how it's made. So you've heard of prohibition, when the government made liquor illegal. So people started drinking other things. And so one of them is called wood alcohol, which is methanol. So what happens is your body takes that and oxidizes it to formaldehyde. So that's bad because you have these amine functional groups in your vision receptors in your eyes. And that formaldehyde condenses with that amine. And once it does that, it makes someone go blind. So during Prohibition, people started to go blind because they were drinking some nasty hooch from, some distillery up in the mountains. So that doesn't happen with ethanol because that gets oxidized to acetaldehyde and it doesn't have the same effect. So just that subtle difference of one carbon atom has profound toxicological consequences on metabolism. So let's see where we're at here. I think I'll skip that one. We got a couple more minutes. So what I want to introduce now is, now that we know how to form the imines and enamines, what can we do with them? We already saw from a prior module, you can take an aldehyde or a ketone, treat it with a reducing agent. That's either going to make a primary or a secondary alcohol. So if we start with our carbonyl, we do a condensation to form an imine. Same concept. There's the double bond. Let's reduce it, because now we have a nitrogen in there. The reducing agent we're going to use for this is a derivative of sodium borohydride. It's called sodium cyanoborohydride. The cyanide is a ligand on the boron that helps match it to the electrophilicity of the CN double bond. And what's a little strange about this, again, this is equivalent to H-, so it's a hydride donor. But you also run this reaction in the presence of an acid, trifluoroacetic acid. So again, that's equivalent to H+. So how can you have two things that would react to form hydrogen in one flask? It's really the presence of that cyanide ligand on the boron. It helps tame the reactivity. But overall, what are we doing? How can I do this? I'm going to draw over this one. I'll call that the blue H. That blue H, cross out that black one there, ends there. And then the red H ends up there. So you're taking an equivalent of H2 and adding it across that double bond. So based on what we're starting with, we're starting with that ketone. We're condensing it with that amine. That's a primary amine. We form the imine, and then when we reduce it, we end up with a secondary amine. And so that's what I mean by higher order. So for now, any amine, A-M-I-N-E, any amine, there's 3 ways you can make it from the different carbonyl amine condensation products through the reductive amination. I think the next mechanism, but basically, just real quick before we run out of time. So this lone pair here on that nitrogen, that forms a bond to the acid, and then that becomes plus. Then the hydride reagent comes along, which is minus, and it adds to that. So overall, you're adding H2 to the double bond. So we'll wrap up there, but next time, like I said, what we're going to do is look at any amine. We'll look at what's bonded to it and figure out the 3 different pairs of carbonyl plus amine conditions we can use to reduce it. Slide was the